I think you probably have seen this Fourier series before in your studies, but let me just start from the here. So, I mean, let's consider a function f. So we are okay. Let me just Fourier series. Okay, so let's consider a function f, which is a function of theta, and theta goes from minus pi to plus pi. Okay, so theta is an angular variable from minus pi to plus pi. Okay, and we assume that this function f of theta is continuous. Continuous and also periodic. Periodic in the sense that f of pi is equal to f of minus pi. So, I mean, think of this picture as you have a circle, and this angle theta is this angle. So, you see the angle goes from minus pi to plus pi. So, that is this angle minus pi to plus pi. And what we are saying is that this function of f of pi, which is as you go from here to here, f of pi is the same as f of minus pi. Okay? So, it's just saying that this function is continuous in this circle completely. Okay? So, this is a periodic functions. Okay? Now, given such a function, you see I can always extend this function. This function is defined only on the circle. So, let me draw it better. Okay. So, here is it's a circle of radius 1. Say, take the radius to be 1. Okay. So, this is a radius 1. And what we are defining is a function only on this circle. Right? But you can always extend this function to some region here. Okay, you can extend this function in this two-dimensional space by the following definition. So, we can extend this function to a region in the xy plane. Okay, which includes the unit circle, which contains unit circle. The unit circle. Okay, and by the following definition, for example, I mean there are many ways of doing it, but as an example, you can take this. So I define a function now as a function of x and y, two variables, because, and I can define this as simply r times f of theta, where these are r and theta are the polar coordinates for x and y. So, in other words, x is equal to r cosine theta and y is equal to r sine theta. Okay. So, I can define a function like that. This function will be continuous in the xy in this domain. I mean, in some region you can define this function. Okay. I mean, you can see that this is continuous because as a function of r, it is clearly continuous. I mean, it's just a linear in r, right? And as a function of theta is again continuous because of this periodicity condition. I mean, these two conditions. We are saying f of theta is continuous in this when theta is between minus pi and pi, and furthermore, it's also f of pi is equal to f of minus pi, right? So you see this function will be continuous everywhere in this domain. So, for example, I can just choose it to be from, I can define this function from say minus 2, I mean take minus 2 to plus 2 x and minus 2 to plus 2 y. Okay? So, consider this square box. Okay? So, I define this function inside this box. Okay? Yeah. Sorry. Yeah, but x is the same as r cosine theta, and I mean, what does it mean? This is at any point I mean, what does it mean, f of xy? I define a function. It means every point in this box, for every point in this box, I define a number, right? A function. Some either real or complex number, whatever your case is. But given an x and a point xy, I surely know what the angle theta and what is the length r, right? And I just substitute this. I just substitute on the right hand side that value r and f, this which is a given function evaluated at theta, right? So it's a function of x and y, or if equivalently a function of r and theta. They are interchangeable. I mean, it's just a different coordinate system, right? Okay. So why am I saying this? So you see now what has happened. So we have a function of x and y, where x and y are in some so now you see in this box what we have is x is between say -2 to +2. Okay. I mean, I just chose -2 and +2, nothing sacred about -2 and +2, because I just wanted to have something which includes this unit circle. So some square which is bigger than 1. That's all. And y is also between -2 and +2. So then I can use the Weierstrass theorem, right? See, Weierstrass theorem is saying that if I am given a function of, say, so Weierstrass theorem we proved only for one variable, right? But you can easily extend it to arbitrary number of variables for the following reason. So suppose, so take the Weierstrass theorem. Which, what was the statement? That any function f of x in, I mean, let me not use the same f, say g of x, any function, g of x, where x is in some interval, a to b, okay, finite interval. It was crucial, it was a finite interval, right? Then I can approximate this function arbitrarily well by some polynomials, right? So therefore, I can always write g of x as some polynomials. I mean, I don't know, say g0 plus g1x plus g2 x square and so on, some polynomials. I can write it like this. I can write, and as I go higher and higher, I can approximate it better and better, right? That will thing. Now, consider a situation where the function is a function of x and y. Okay. Well, I can think of this as keep the x fixed, and I just think of it as a function of y. So here again, x is between a and b, and say y is between some c and d, finite intervals. Both x and y are in finite intervals. So think of this as a function for a fixed x. You think of it as a function of y. So keep x fixed. Okay. Then what I'm going to do by using Weierstrass theorem, I will find again some let me call it f now. I will find f naught plus f1 y plus f2 y square and so on and so forth for a fixed x, right? But of course, as I change the x, these coefficients will change, right? So that means these coefficients are functions of x, right? Now you apply the Weierstrass theorem for each of these functions, right? So f naught can be again expanded in terms of polynomials of x, f1 can be expanded in terms of polynomial of x, and so on. So the final result is that I can expand this in terms of a double sum. So fn m x to the n y to the m, right? And I mean, I can consider this to get better and better approximation. Of course, I have to increase the order of the polynomials, right? But that's what the Weierstrass theorem is saying, that you can arbitrarily well approximate. So I mean, although we proved it only for one dimension, I mean one variable problem, this extends to any number of variables. We just systematically apply the same thing over and over again. So it goes through. So the upshot is that I can expand this f of xy in this way, because you see both x and y are in a finite range, finite interval, right? So I can use the Weierstrass theorem to expand it like that. Okay. Fine. Now let us look at, I mean, in fact, we are interested in r equal to 1. I mean, okay, let's substitute back x and y in terms of, in the polar coordinates, r cosine theta and r sine theta. Okay. So what we find here is that you get f of xy is equal to some coefficients f and m, r to the power of n plus m, cosine n theta, cosine to the theta to the power of n, and sine theta to the power of m, summed over n m. Okay. Now, in particular, let's look at r equal to, I mean, since f theta is given by simply f of x phi evaluated at r equal to 1, unit circle, right? So when r is, so therefore this comparing this with that equation, we see that f of theta is simply this f n m cosine theta to the power of n sine theta to the m. Yeah. So this shows that you can approximate any function of theta, which is a function which is periodic in theta. I can express arbitrarily well by considering such polynomials. I mean such terms, trigonometric quantities, cosine theta to the n, sine theta to the m, and to get better and better accuracy, I may have to go to higher and higher powers of n and m. I mean higher values of n and m, right? I mean, so this n says goes from so 0 to capital N, and m goes from 0 to capital M, right? To get better and better approximation, I may have to increase this value of capital N and capital M. But what Weierstrass theorem says that, I mean, by choosing this capital N and capital M large enough, you can get as close as you wish to the f of theta, right? That's so this is just the application of Weierstrass theorem, right? But now I can rewrite it in a more convenient way, because after all, cosine theta in terms of this, after all, cosine theta is e to the I theta plus e to the minus I theta divided by 2, and sine theta is e to the I theta minus divided by 2i. So I can just plug that in here. So then you see it will be just e to the power of I theta to various powers, right? So I can rearrange this thing. I can rearrange these terms as a series in e to the power of I n theta, and I call it fn, where n goes from minus infinity to plus infinity, right? I mean, take this to infinity, because if I increase to infinity, then I can get, I can make it exactly equal to that. This is minus infinity also here, because you see that there is also e to the minus I thetas. So when I take the products, I will start getting e to the power of minus I times any integer, right? So any positive or negative integers will come when you take the products of this. I mean, you have to take this to the power of n and this to the power of m, right, in that term. And when you multiply these two things and open the brackets, you will get terms which will be like all the way starting from e to the power of I times n plus m theta, all the way down to e to the minus I n plus m theta, right? So that's why you have both positive and negative integers sum. So this is the kind of reason why we expect that this function of f of theta, I should be able to express it as a linear combinations of this e to the I n theta. Okay. In fact, this e to the I n thetas are actually, I mean, they are in fact orthogonal polynomials actually. I mean, orthogonal functions on the circle, right? Why? Because if I take e to the I n theta and e to the I m theta, okay, and integrated d theta from minus pi to pi, then you see this is proportional to delta n. So let me write it like this. Better write it like that. So think of this as a basis. En is simply e to the I n theta, up to some normalization constant. So up to some number here, which we will determine by demanding orthonormality. So at the moment is some constant here. So now let's compute En with Em. Okay. Yeah. No, but now I look. Yeah, I mean here it was. Originally it was, right? Yeah, but now I specialized to r equal to 1 case. f of theta, yeah, I use this equation here, because at r equal to 1, f of xy is simply f of theta, right? That's how I'm defining it. Because f of xy was what? It was a, I mean, you are given first of all a function on the unit circle, right? F of xy is just arbitrary extension, right? Arbitrary but just continuous, that's all. You want continuous function such that its value on the circle is the same as original f of theta, right? So you're extending it. So once I substitute r equal to 1 here, then you're getting back f of theta, right?
I mean, the next result, f some, he's saying when we expand f of theta in terms of e raised to n theta, we have coefficients fn, and are they really functions of x and y?
Ah, these coefficients fn. No, no, these are independent of x and y. These are constants. I mean, these are all constants, right? In the Weierstrass theorem, this when I expanded as f and m, x to the n, y to the m, those f and m were constants, right? And now this here is just a one fn because I have rearranged these sums. These terms I have rearranged it by expressing cosine theta and sine theta like this, and collecting the say the coefficient of e to the I n theta. Okay, so that's this. Going from here to here, I have rearranged this sum. So these fn's are not the same as f and m. I mean, there are some complicated combinations of f and m. Okay, so if I compute this integral with a weight function 1, I will always choose weight function 1 in this case. Then this is simply well, e to the I n theta from here. For em, I have to take the complex conjugate. So you get here e to the minus I m theta. Okay, let me put here some alpha n. Alpha n is some constants. So here you get alpha n, alpha bar m. Okay, and then d theta integral from minus pi to plus pi. So this integral you can perform. This is what e to the power of I n minus m theta d theta minus pi to plus pi. Now there are two cases. One when n is equal to m, and the other case when n is not equal to m. Okay, so in the first case, let's say n equal to m, this just becomes 1, and the result of the integral is simply 2 pi, right? So this gives you 2 pi alpha n mod square, because m is the same as n, right? So alpha n mod square. And when the second case, when n is not equal to m, I can integrate this. So this will give me when I integrate this, I will get 1 over I times n minus m e to the power of I n minus m theta evaluated between pi and minus pi, right, times alpha n alpha m bar. Okay, and that is 0 because this is periodic function, right? The value theta equal to pi, this is the same as theta equal to minus pi, periodic function. So this becomes 0. Okay, so we are saying the answer is 0 here. So you see, indeed, these are orthogonal to each other. So n is not equal to m, it is 0. And when n is equal to m, it is 2 pi alpha n square, mod square. So I can even choose alpha n to be simply 1 over root 2 pi, and then it will be orthonormal. So it's an orthonormal set of functions.
Why we choose the phase to be 1?
Which phase?
I mean, alpha, the phase.
It doesn't matter really, no. I mean, if you put a phase here, I mean, so some phase, some constant, I beta, let's say, something, some constant, that I can absorb it in the theta itself. I mean, it's not important actually. Okay, if you wish, you can do it, but it's not important really. Yeah. I mean, that will be just unnecessarily complicating because you'll have to keep track of that beta everywhere, and there's no point in doing it. You don't gain anything from that. Okay, so this is the thing. So now let's see. So what can one say here? I mean, I will just, I think without proving, I will just, or maybe I just give a proof of one statement. And, okay, I'll see how it goes. There are certain things you can ask. So, okay. So given this, you see En, we remember the proof. I think this was discussed several weeks ago, so I don't know whether you remember that. There was this statement when we looked at this L2 spaces, right? L2 some W spaces in some interval A to B, right? Then we said that if there is an orthogonal basis, orthogonal is sufficient. Orthogonal basis is given to you, suppose. So n is, n equal to whatever 1, 2, 3, etc. I mean, infinite. This is a basis. Let's say is an orthogonal basis. Okay, then and if you give me any function f, any state, any vector, let's say belonging to this space, then if you consider this expansion f, let's say this vector fn, first of all compute this quantity f en, okay, and let's call this numbers as some fn, okay. This will be some, this is some number, okay, which I call fn. Okay. Then consider these vectors fn en, summed over n going from 1 up to some number, say capital N. Yeah. Yeah, here I've chosen the weight function 1. Yeah. Yeah. So this discussion is only for weight function 1. This entire thing is now, all this Fourier series I'll be using always weight function 1. If the weight function is not 1, it won't be orthogonal. Yeah, exactly, it won't be. Yeah, in general it won't be, right? If you put some function, suppose weight function was, I don't know, sorry, theta. But then you want to choose something which is periodic, right? After all, we are considering periodic functions, right? No, weight function, yeah, but you also want to be periodic, right? Because the whole discussion is about the periodic functions. Theta equal to minus pi and theta equal to pi are the same points on the circle, right? The Fourier series is useful for really periodic objects which are, you should think of theta as an angular variable, right? So I think that the only periodic function which, I don't see anything else you can choose which is 1, which is not 1. No. But at least let's say I'll be specializing to just this case. W weight function for this entire chapter will be always 1. Huh? Yeah. Okay. So we know that. So let's call this vector as some f capital N. Okay, this sum. Then we have seen the theorem which says that this sequence of these vectors converges to the original vector f, in the sense of in the L2 sense, in the sense that what we saw was that limit n goes to infinity of these vectors fn is equal to f, but is equal to in the sense that almost everywhere, right? Or in the mean, it's almost everywhere. So this we saw. Okay. So now here I have. So let's specialize this to this case here. Now we have this orthonormal basis of these functions, and so I can express any function f which is in the L2 space. So take any function f of theta, which is in the, I'll write it in terms of this vector f, which is in the L2. See, the weight function is 1, so I take weight function equal to 1. For this discussion, weight function is 1, right? So I take L2 1, and the interval is minus pi to plus pi. Right? If I consider any function, any f which is inside this space, which means it's square integrable, right, in the Lebesgue sense with this weight function 1. Then I should be able to expand f as this fn en, okay, summed over n. Okay, I should be able to do that. But again, this equality will be in the sense of the L2 spaces. This will be always almost everywhere. This is almost everywhere. Okay. It's a bit. As I mentioned to you, this is a bit of a weaker statement. See, Weierstrass theorem itself was a much stronger statement. That the polynomials was converging to the functions, really, I mean, completely to the functions. It was not just almost everywhere. It was not that at some, some countable number of points, the answers were very different. It was not the case. They were all converging to the actual value of the function at every point, right? Uniformly, it was converging. So that's a much stronger statement than this statement. This statement is a weaker statement. Okay, it's just saying that it is converging almost everywhere to the original function f. But at some measurable number of points, I mean, countable number of points, which is the set of points whose measure is 0, whose Lebesgue measure is 0. That's what I mean. The function may be different. The result here may be different from the function here. No? So that's a weaker statement. So one would like to ask this question to understand a bit more. Can we say a bit more than this? I mean, this was guaranteed to us, but can we say more than this? Can we say really about the function itself, whether the series converges or not? So there are some theorems about it. Let me just, I will not go through the proofs of this. I mean, in fact, even in the notes, even in the book, the proofs are not given. So I'll just state the theorem. Okay, so one statement is the following. So let's suppose the function, so that one theorem is this. Let's suppose the function f and its derivative. It's the derivative df by d theta, both are continuous. Okay, and f is periodic. Okay. So here we are putting a lot of conditions. It's not just that the f is continuous, but also the derivative is continuous, we are saying. So we are requiring much more from the function. Then the theorem is, then the statement is that this series converges. So, so 1 over root 2 pi. So if I take this minus infinity to plus infinity, fn, where fn is just the integral 1 over root 2 pi f theta e to the power of I and minus I n theta d theta minus pi to pi. Okay. I mean, this is what in this notation we would call ENF, right? This is what it is, right? This integral. So you have to take the dual vector, so it becomes complex conjugate e to the minus I n theta, right? And then integral f theta d theta. W, the weight function is 1. That's why I don't have the weight function here. It's just 1. Okay. And this 1 over root 2 pi is simply coming from the normalization here. Okay. So then the statement is this series converges. So this series where fn is equal to that converges uniformly to f of theta. Okay. That's the statement here. I don't know, maybe I can give a proof of this statement. It's not too complicated. Let's give a proof of this. Okay, so first of all, let's start from this df by d theta. And so consider, so the df by d theta again, so f of theta will be, these are all, I mean, it's a continuous function, so these are all, I mean, I will use sometimes this vector notation, right? What do I mean by vector? When I use a vector notation, what it means is that I'm thinking of this as a vector in the L2 space. Okay. So vector in the L2 space already you see is a bit weak statement, because two different vectors, I mean two different functions which differ from each other at a countable number of points is actually the same vector in the L2, right? L2 space, you have to identify these two different functions, right? So this already is a bit weaker than that. There is a very precise function. A function is given to me, but when I'm writing like this, it's a bit in the weaker sense. I mean, any function which could differ from this function f on a countable number of points will define the same vector. So this is the point to remember. So f of so similarly for df by d theta, there will be a corresponding vector df by d theta in the L2. So these are in L2 spaces. Okay, I will drop this. Okay, minus pi to pi. Okay. Then let's consider this df by d theta. I can always express it, write it in terms of this quantity En df by d theta summed n En, right? I mean, this I just use the theorem which I mentioned just before, right? Given a vector in L2 and an orthonormal basis, okay, I can always write it as some numbers, some coefficient times En sum, and that coefficient is given by this, right? That was the statement. So this series will converge in on almost everywhere to this df by d theta, right? That's what it's saying. Okay, so let's compute now this quantity. Okay, so what is this quantity? En df by d theta is by definition the integral d theta e to the minus I n theta 1 over root 2 pi and df by d theta minus pi to pi. Okay. Now you can do this integration by parts, okay, and use the fact that f is periodic. Okay. Of course, this is obviously periodic. So the boundary term will be periodic, right? And so they will vanish. So therefore, I can do this integration by part, and I get here minus 1 over root 2 pi minus pi to pi. Now the derivative hitting this one, right? But that just simply brings down minus In. So there is a minus, so minus minus plus In times d theta e to the minus In theta f. Okay. But this is what we called, this combination is what we call Fn, right? I think I was using superscript. This Fn was that. Okay. So what we are seeing is that this quantity is in fact equal to In times Fn. Okay. So this the conclusion is this is simply In times Fn. Okay. So okay. Now let's compute. Now you remember this again. I think this was probably some time back, so maybe you might have forgotten about it. There was this one of the again another thing that we proved was that if you take the norm of this vector square, norm square of this vector, that's the same as the sum of the mod square of these coefficients. Correct? Right? If you remember that. I mean, that in some sense you can see that if I just take a norm square of the df by d theta, then it's just going to be the squares of this, because these are anyway orthogonal to each other, right? So it's going to be equal to the sum of these coefficients, but these coefficients we already computed, In, Fn, right? So I take the mod square of that, so you get here n square, Fn square. Fn mod square summed over n. Okay, this was what we call, I think we were calling it this Parseval relation, right? I mean, generally there was a bound that this is greater than or equal to this, right? But if it is equal, that means we really have a complete basis, right? That was a statement we had. I mean, this was some time back, but you might have forgotten. I'm just trying to remind you. Okay. But on the other hand, df by d theta is in this L2 space. We said this in L2 space. So this is finite, right? That means this series is finite. I mean, this series converges to some finite number, right? It's something finite. So it is certainly less than infinity, finite quantity. Okay. So what this means is that if I take, I mean, so the fact that this is converging, you remember this one of the criterion, Cauchy criterion for a series to converge, is that, so this implies, the convergence implies that the sum n square fn square sum from k n equal to k to say L will be 0, will go to 0 for k and L large, correct? This was one of the criterion, the Cauchy criterion. Do you remember? I mean, so what you do, you consider the partial sum up to n equal to k, right? Then you consider the sequence of this k, right? The condition for the convergence of the sequence was that say fl minus fk mod goes to 0 for L and k sufficiently large, right? That was the condition. So I mean, the convergence implies that for sufficiently large k and L, you can make this arbitrarily small, right? In fact, to 0, right? So for sufficiently large k. Okay. Okay. Now let's go back to now the original point, right? So we wanted to look at. So we want to go back and look at the original function f, and so we are asking whether this fn. See, remember this was what we wanted to check, whether this quantity fn e to the I n theta summed, this converges to f or not, right? I mean, really converges to f or not. So let us look at again. So if it converges for the same reason, so if this sum converges, then by Cauchy criterion again, you must have fn e to the I n theta summed n equal to k to L mod square must go to 0, right, for sufficiently large k and L, for large k L, right? Again, the same criterion. Right? Okay, so let's look at this. What is this quantity? I mean, we want to show that this goes to 0, right? But let's see what it is. So this is the same, and so this is I will write it as, of course, this is less than or equal to. Now use this fact that the mod square of the sum is less than or equal to the sum of the mod square, right? So when you take the mod square here, so this is less than or equal to sum n equal to k to L, mod square of individual terms, right? But e to the I n theta mod square of e to the I n theta is 1, right? So you just get mod square of fn. Okay, that's what it is. Okay, now let's do this. Let's do the following. Let's multiply and divide by n square. I have done, I mean, no change here, right? I just multiply. That's the reason why we have this. Okay. Okay. So you have this quantity and then you have this quantity, right? So now you can think of this. I mean, think of this as a what shall I say? I mean, so this is going to be from this what is it called? Cauchy-Schwarz inequality, right? From Cauchy-Schwarz inequality. This is less than or equal to the sum, let us say n equal to k to L of this quantity Fn square n square times the sum of this L, not n, let me put here m, 1 over m square. Okay. Is that clear from the Cauchy-Schwarz inequality this time? Okay. So think of this as a, I mean, so this is, there are I mean L minus k components here, right? This, think of it as a vector which is L minus k dimensional vector, whose components are 1 over n square, that's one vector, another vector is Fn square n square. So this can be thought of as dot product of these two vectors. But the Cauchy-Schwarz inequality says that the dot product of these vectors, it should be less than or equal to the product of the lengths of individual vectors, right? So the first vector was this, so its length square is that, its length is that, and the second vector is this, its length is that. Okay. So here I've used the Cauchy-Schwarz inequality. Okay. And now use this fact here. This I can make arbitrarily small, the first term, right? And the second term, this series we already know converges. The sum over 1 over integer 1 over n square, that converges. You remember that? I mean, I don't know this. So there's a sum over 1 over n square. This converges. Okay. Whereas sum over 1 over n doesn't converge. This does not converge. Okay. This 1 over n square converges because of the simple reason. I mean, as n goes to infinity, this goes to 0 much more rapidly than that, right? It's for the same reason. If you think of it, I mean, for large n, you can think of it as integrating, right? So think of the sum is the same as integrating, right? So this is like dx divided by x square. Dx divided by x square at x goes to infinity is perfectly well defined. No problem with that. Whereas this is dx over x, whereas logarithm. So it's a logarithmic divergence there. Okay. So this is convergent, that is not convergent. However, what we have is actually this one. Since that series converges, again by Cauchy criterion, this can be made arbitrarily small, right? So both of these quantities can be made arbitrarily small. Okay. And you see that is completely independent of theta, right? That means that this series converges. First of all, we see that this series converges, and secondly, it converges uniformly because it's independent of theta. Right hand side is independent of theta, right? Yeah. Sorry. Yeah, sorry, there's a square root. Yeah, correct. There's a square root indeed. You're right. Yeah. But I mean, it's just, again the same thing. Each of them is going to 0, right? So they're the same thing. Yeah. Okay. So now, so the conclusion is that this series converges uniformly. When you have uniform convergence, you see you can commute many things, right? Remember we discussed the integration you can commute, right? So same way continuity also, the notion of continuity also commutes. Okay. The statement is that if I have given a series, so if I'm given a series, so here what we have is Fn e to the I n theta. Okay. So 1 over root 2 pi. Okay. This series is we are saying, suppose this series converges uniformly, then the function to which it converges will be continuous provided each of these terms is continuous, right? But this is obviously continuous. E to the I n theta is a continuous function, right? I mean, remember that we discussed that when you have a uniform convergence, so let's say this converges to something, some function, let's call it g of theta, okay? Say this converges. Then, for example, I can integrate, the result of integrating g theta is the same as the result of integrating each of these terms separately, and then summing up the results of individual terms, right? Which is only, I mean, only when you have uniform convergence you can really do that. In general, if it's not uniformly convergent, you cannot commute these two operations, integration and the sum. Same way, the continuity also is a kind of, you can commute the two things. If individual functions are continuous, right, and if this series converges uniformly, okay, then the resulting function is also continuous. Okay. So, as a result, g of theta is continuous. Okay. That's because of uniform convergence. Otherwise, we cannot be sure about it. It may converge, it may be continuous sometimes, it may not be continuous sometimes, but we cannot be sure about it. Yeah.
Can you say why it's continuous again?
I mean, it's again it's due to the fact that it converges uniformly, and the reason is more or less is easy to see. I mean, so look at I mean, evaluate this thing at theta and some theta plus epsilon. Okay. It is going to converge to some g of theta and g of theta plus epsilon, right? But the rate of convergence is uniform, so it's independent of theta, right? So this is the main reason. I mean, it's not a proof. Okay, I'm not giving a proof of that statement, but essentially you can prove it in this way. Because the reason is that you can make, I mean, you can find some for any given epsilon, right? Any given epsilon, you can find some capital N, okay, such that you can, I mean, so what am I saying? What do I mean by this? We are saying, so therefore it's let's consider the partial sums, n equal to whatever, up to some capital N, okay? So consider the sum up to capital N, okay? And define this function as gn theta, whatever the result is. Okay. Then uniform convergence means that for any epsilon, you can find there exists a n, which depends of course on epsilon, but not on theta, such that g of theta minus gn of theta can be made less than epsilon. Okay. But that's independent of theta, that's the point. So then using this, you can now look at the situation. I change the theta a little bit, okay? Then again, you see the difference between, so gn of theta plus epsilon, okay, will be this fn e to the in theta plus epsilon, okay, sum. And once again, you can because uniform convergence for the same capital N, you see the difference between this and that, I mean this and the g, final g, I can make it arbitrarily small, right? So I mean, in some sense, the reason why something does not give you finally discontinuous functions is because, I mean, something must go wrong with it cannot be uniform convergent, right? Because individual functions are continuous, right? So how can finally the result be a discontinuous function? That can happen only if it's not uniformly convergent, right? Okay. Of course, it can happen other way, meaning that sometimes maybe it's not uniformly convergent, but still the function is continuous. That can happen. Okay. So the conclusion is that this result, whatever it is a continuous function. Okay. But on the other hand, I know that this function, by the general theorem, I know this must give you f of theta almost everywhere, right? In the sense of the L2 space. This we already know. So the difference between f and g must only be on a countable number of points, right? But f is continuous by assumption, so f must be equal to g. Okay. So the statement is that, I mean, so f theta must be equal to g of theta almost everywhere, which means these two are the same except for some countable number of points. Okay. But on the other hand, this is continuous and that is continuous, So the only way that can happen is if they are exactly equal everywhere. Okay. Yeah. So I think that is the basic statement. Okay. And so in this proof, you see, it was assumed something which is df by d theta is continuous, right? That was the crucial point here. Okay. That's why we got the bound that n square fn square converges, right? That's how we obtained that. But in fact, if you look at the way we have proven, it is not that we have really used the fact that df by d theta is continuous. It's not really we have used. I mean, all we are demanding is that this guy must be in the L2 space. Okay. So it should be integrable in the sense of Lebesgue, not necessarily in the sense of Riemann. When you integrate using the Riemann sense, that is when you use you need continuous function, right? But otherwise, so some of these conditions you can make it weaker. The conditions, you don't have to make such a strong condition. Okay, and that is what finally, I mean, various mathematicians tried to weaken these conditions. So I'll just state the final form of the theorem without a proof. Okay. So, and this theorem is much more powerful because this is valid even for original functions f which are not continuous. I mean, so far we have been talking about functions f which are continuous and periodic. But the final theorem which comes out is much more stronger than this. So the theorem is the following, that theorem. Maybe I should first define what is a bounded variation. So the functions f will allow discontinuity also. Okay. So let's say the Fourier series. So the theorem. So let's say some function f of theta is given in the same interval minus pi to pi. Okay. And but this function, I mean, I'm allowing discontinuities and so on, but not too much. I mean, if it is a very violent discontinuous, then we cannot do much about it, right? So a particular type of function which is called, I'll just define what it means. So this function is of bounded variation. So f is of bounded variation. Okay. So what this means is a bit strange, but anyway, that this function f, this means that this function f can be written as a sum of two functions, okay, where this function f1 is, say, non-increasing, and this function is non-decreasing in the entire interval minus pi to pi. Okay. So if I'm able to write a function, any given function, as a sum of two functions where one of them is non-increasing, other is non-decreasing. Okay. Okay. It looks like it's always possible, right? Yeah. But the point is that this, in fact, this implies the following statement. This implies, which again, I'm not going to give a proof, but this implies that even if this function f is discontinuous, okay, it is of the following type, that for each theta, for all theta, you can define f of theta plus 0 and f of theta minus 0. Okay. Yeah, what does it mean f of theta plus 0? Meaning that the limit as I come from the right, take theta plus epsilon and take the limit epsilon goes to 0, that is defined. Okay. Similarly, here theta minus 0 means theta minus epsilon with epsilon goes to 0 limit, again it exists. These two exist, that's the point. Huh? Okay. They may be different from each other. Yeah. Non-increasing. One of them is non-increasing, other is non-decreasing. Sorry? No, this is the definition of the bounded variation. I'm saying this is the definition of the bounded variation. If I can express f as a sum of two functions, where one of them is non-increasing, other is non-decreasing, then I say that this function f is of bounded variation. This is a definition. Okay. I mean,
If we say f1 is not increasing, then does it mean that f1 can decrease?
no. When you say non-increasing, yeah, non-increasing means it can decrease, of course, right? So I mean, think of this picture. Yeah, I mean, here you have, so say minus pi to pi, right? So f1 is non-increasing, so it could be anything. I mean, it could be something like that. It could be, could be a discontinuous function. Doesn't matter. But the only condition is that it should not be increase. As I increase the x, theta, right? It should not increase. Right? Similarly, f2 is some function which is non-decreasing. So that means it can only increase, it can stay fixed, it can stay increase, but not decrease. So this could be something like that. Maybe it's even discontinuous. Maybe from here to here it jumps. Maybe here it goes like that. No, this kind of thing. So provided you can express f as a sum of these two functions, okay, one is non-increasing, other is non-decreasing, then this function f has this important property that at each theta, the right limit and the left limit exists. They may be different from each other, okay, but the right and left limits exist. That's the point. Yeah? So if the function f is a bounded variation, then the theorem says that the Fourier series, by the way, that is called the Fourier series, what we were writing so far. Fourier series f of fn e to the I n theta 1 over root 2 pi summed over n, where fn was this Fourier coefficient. This is called Fourier coefficients. This is 1 over root 2 pi e to the minus I n theta f theta d theta. Okay, so these are called Fourier coefficients. Okay, and this is called Fourier series. So then the statement is that this Fourier series, in fact, converges to a function let's say it converges to f of 1/2 of f of theta plus 0 plus f of theta minus 0. Yeah? So this is for a given theta. This is for theta between minus pi and plus pi. So this is one statement. And second statement, at theta equal to, you can ask now at what happens at theta equal to pi. At theta equal to pi, it is simply half of f pi plus f of minus pi. This is at theta equal to pi. Pi or minus pi, plus or minus pi. So see it's much, it's a very strong statement actually. I mean, if you think about it. You see here, I'm not even demanding periodicity. If it was periodic, of course, f of pi is equal to f of minus pi, right? Then this just becomes twice f of pi. You divide by half, so it gives you back f of pi. Yeah? So you see what this theorem is even applicable for non-periodic functions and also discontinuous function. I mean, if the function was continuous at theta, at a given theta, these two limits are the same, right? I mean, that's what you mean by when you say continuous. It's not, the two limits are the same. Left limit and the right limit are the same. In that case, these two are equal, which is equal to f of theta itself. So twice f of theta divided by 2 is f of theta. So what this is saying is that in all those points where original f is continuous, there this Fourier series gives you back that same function, right? But the places where this f is discontinuous, what this Fourier series, the result of the Fourier series gives you is actually the average. And similarly, if the function is not periodic to endpoints, it just gives you the average again at endpoints. So that's the statement. Now this is complete. I mean, it's not. I'm not talking about almost everywhere. This is the exact result. I mean, this is what comes out as a function. Okay. So maybe okay. So I just give you an example of computing this Fourier series. And in fact, to show these statements, that the place where there is discontinuity, you find the average. The result is an average. Okay. So let's give you this. Okay, what is worked out here? So example. Consider f of theta to be the following function. It's a step function actually. So 0 and 1, 0 between, say, theta between 0 and pi, and 1 between, say, minus pi theta 0. Okay. Yeah. So I consider such a function. So this is a step function, right? And it doesn't, I mean, okay, this. So if you draw it, here is minus pi, this is 0, that is pi. If you draw the function, here it is 0, right? And here it is 1. Okay. So there's a discontinuity here at 0. In fact, it's the discontinuity at 0 as well as it's not periodic, right? So we can check both of these statements. So let's compute this Fn coefficient. So Fn coefficient is simply this f of theta, so d theta, f theta, e to the minus I n theta, 1 over root 2 pi, minus pi to pi. Okay. Now this integral, I mean, from 0 to pi, f is 0, so that part doesn't contribute. So this integral is simply 1 over root 2 pi minus pi to 0 d theta, but f here is simply 1. So I just put 1 there, and then the integral is simply this here. Okay. Now this can be, so there again I have to consider two different cases, n equal to 0 and n not equal to 0. When n is equal to 0, this gives you just pi. So f0 is simply pi divided by root 2 pi, so that is root pi by 2. Right? And for n not equal to 0, f of n is, you can do this integral, so this gives you 1 over, so let's do that. So this result is 1 over root 2 pi, and here is 1 over minus I n e to the minus I n theta, evaluated between 0 and minus pi. Right? So at 0, this is 1. So what is that? So at 0, this is 1 over root 2 pi, 1 over minus I n, and at 0 it's 1, and minus pi, it is e to the I n pi, which is minus 1 to the n. So this is minus 1 to the n. Okay. So what this is saying is that if n is even, this cancels, and when n is odd, this gives you a factor of 2. Right? So let me just summarize it here. So Fn is, sorry, sometimes Fn for n not equal to 0. This is equal to 0 for n even, and it's equal to, this gives, for odd it gives you a factor of 2. So, okay, 2 over root 2 pi times minus I n for n odd. That's the result. Yeah.
Can you please repeat what you have said when you are changing the limits from negative pi to pi to negative pi to 0? I've not understood.
You mean this one, this part, this line? No. From here to here?
Yes.
Because f we said is 0. From between 0 and, I mean, this integral I can write as minus pi to 0 plus 0 to pi, right? But from 0 to pi, this value of f is 0, right? So therefore, that integral will give you 0. So the only thing is that, and in this interval, f of theta is 1, right? So I just substitute 1. So that's why there's a 1 here actually. Okay. So let's then write down the sum. So we want to write down Fn e to the I n theta, 1 over root 2 pi. We want to write down the sum. So first of all, f0 term, f0 is simply gives you root pi by 2. Okay. And then you have the odd, so remaining fn's only odd ones contribute, right? So you get here n equal to odd. So there will be two terms. I mean, you have n positive. This is, you see, this is going from minus infinity to plus infinity. Remember, this n is over all integers. So you have positive odd and negative odd. Both are non-zero, right? So you get here, so 1 over root 2 pi. Let's say put here 2 also. So you get here 1 over minus I n times e to the power of I n theta, right? But I can combine the positive n and negative n together, right? I mean, here n is both positive and negative. Okay. So for example, n equal to 1, n equal to minus 1, n equal to 3, n equal to minus 3. But what will happen if I take n? So if I take n and minus n, when I exchange n with minus n, I will get here e to the minus I n theta. But this picks up a sign plus I n now, and I have to add these two things. And now I take n positive, because I have summed already, both taken into account the negative guys. Okay. So this gives you, so what is this? This is so minus I n e to the I n theta minus e to the minus I n theta, which is 2i sine n theta. Okay. So putting that all together, so you find here this is root pi by 2. What is root pi by 2? Now I still have to divide by 1 over root 2 pi. There is a 1 over root 2 pi outside. Huh? So what do we get here? Root 2 pi. So that gives you 1/2. Right? I mean, root pi cancels. Root 2 makes it 2. And then here you get plus 2 over 2 pi. And then here I cancels. There's another factor of 2 and the minus sign. So minus 4 sine n theta divided by n. Summed n positive and odd. Yeah, you're good.
For example, theta, our function is not continuous at 0.
Yeah, but I mean that doesn't matter. You can either think in terms of Lebesgue integral. I mean, it doesn't matter because this point is of measure 0. This is just one point. It's a measure 0 set. But even without Lebesgue, I mean, such functions you can even integrate by Riemann integrals. So provided so you can always integrate piecewise. You know, if let's say there is a path, there is a interval where there are subintervals in which the function is continuous. Okay. But not across as you go from one subinterval to the next subinterval. But then you can write the full integral as the integral over the subintervals, right? In each subinterval, it's a continuous function, so you can just use Riemann integrals there. But 0 is a point. I mean, the 0 point. We said that even the infinite number of points, provided they are countable, they have zero measure, right? Here is just one point. So any finite number of points or any countable number of points, if there is discontinuity, Lebesgue integral always makes sense. But what I am saying is that even Riemann integral makes sense, you know, by defining it, by generalizing it a little bit and making it piecewise integrals. You integrate by pieces. No? In each piece, function is continuous. Okay? The two will be the same. Lebesgue integral will give you the same answer. For the reason that Lebesgue integral for measure 0 set, it doesn't contribute anything, and a point or infinite number of points are countable, they are measure 0 set. Okay. So yeah. So finally, this is the answer. Okay. This is what we are saying. The Fourier series is. But now let us try to compare to see whether what do you get? I mean, do you get back the original function or not? Okay. So at theta equal to 0. You see, at theta equal to 0, all these guys vanish, right? Because n is odd. Huh? Well, actually, even for n not odd, it's still 0, right? And here, so what is left over is simply half, which is exactly the average of 0 plus 0 and 1, right? Similarly, if you compute at theta equal to pi, okay, at theta equal to pi, you find sine of pi theta is 0 again, right? So this all vanishes, you get half, which is again the case because f at pi was 0, f at minus pi is 1. So this gives you average of that, right? So it's exactly giving you the average. Now I have not proven that this gives you the original function for all the different values of theta. I mean, I'm just looking at the discontinuous, right? This is maybe I just leave this as an exercise. I mean, try to show. Maybe it's a little difficult, but okay. You can try to do this. Try to sum this series for theta, for arbitrary theta. Okay? Don't take theta equal to 0 or pi because that you don't need to sum. It's 0 already. This sum is 0 anyway. Only thing is what survives is 1/2, right? So if you can try to do for theta not 0 or pi, but arbitrary, okay, and try to see if you can sum it up. But I mean, there are various tricks of doing this. Okay, maybe I'll come back to this at something. I'll try to show you in some other example maybe. Okay. Let's take another function, which is let's take another example. Because I mean, I give you another example to show that now that you are convinced about this theorem, you can actually get lots of identities. I mean, if you accept this theorem, which has been proven mathematically rigorously, but if you accept this theorem, you can get lots of identities from the Fourier series. Here itself, I mean, if you accept this identity, then this tells you that for any value of theta, this Fourier series should just give you what that original f theta is, right? In the places where it's continuous, you should just get that, right? And where it's discontinuous, it just takes the average. So it gives you infinite number of identities. For example, if what this is saying is that theta is between 0 and pi, strictly between 0 and pi, okay, where it is continuous, there f is 0, right? So that means that this sum should become independent of theta in this range, because for any value of theta between this range, answer is fixed, answer is constant, 0. Okay? So what it says is that this sum should give you exactly half to cancel that. For any value of theta in this range is independent of theta. You see? And similarly, if you take the other range, theta between minus pi, strictly between minus pi and 0, then this answer is 1, which means these two things should add up, right? So it's giving you identity, in fact, infinite number of identities, because for each theta this is true, right? Okay, so, but it will be also good to see if to convince yourself that this is really true. Okay, let me take another example, which is again worked out here, but I will try to work it out in a slightly different, okay, not very different way, but okay. F of theta is this, theta square between 0 and pi. And let's take and it is equal to 0 between minus pi and 0. Suppose I consider this function. It's slightly different from the example given here. I mean, the example given here is not about that. It just takes this function 0 to pi. Okay. But I will come back to that point a little later. So if we consider this again, and let's consider Fn. Let's consider Fn. So this gives you again 1 over root 2 pi, minus pi to pi of f theta e to the I n theta d theta. But again, for the same reason, you see, in this from minus pi to 0, f is 0, so that part will not contribute. So this will simply give you 0 to pi. And here, f of theta is theta square, so it gives you theta square here. Okay. So now you can start doing partial integration. So for example, you can write this as d by d theta of 1 over I n e to the I n theta and do the partial integration. But now you have to be a little careful because this function is not periodic. So we have to do this. I mean, there are lots of terms here now. So you have 1 over root 2 pi. First integration by parts gives you in here. I mean, this is for n not equal to 0. Of course, for n equal to 0, you cannot. N equal to 0 is more easy to calculate, but I'm calculating n not equal to 0. So 1 over in, and so there will be one boundary term which will be theta square e to the in theta, evaluated between pi and 0, right? And then the other will be so minus, when a derivative hits here, it gives you 2 theta, right? So 2 times d theta theta e to the in theta. Yes, 0 to pi again. Okay. Once again, write the same thing again, 1 over in e to the in theta d by d theta, and do the same thing. Okay. So do the again integration by parts. So there will be a boundary term, and that boundary term now will be an extra. So there is an extra minus this in minus 2 over in. Sorry, this should be minus in, right? So I should change n to minus in. So this is minus in. This is minus in. This is minus in. And there is a minus here, and then I have to take theta e to the minus in theta. Okay. Again, evaluate between pi and 0. Okay. And then the derivative hitting this guy, but that is 1. So the sign has changed now. So you get plus 2 over minus in d theta e to the minus in theta, 0 to pi. So you see there are many terms now. Actually, so what do we get, the final answer? So first of all, this one. So this one at pi, theta equal to pi, this is simply minus 1, right, e to the minus no, I mean minus 1 to the n. Okay. So the first, so there's a 1 over root 2 pi. Okay, there is a minus 1 over minus in, and here you get pi square times minus 1 to the n from there. And lower limit doesn't contribute because theta equal to 0 there. Then here again there is an extra minus 2, so plus 2 over in from here, and you get pi times minus 1 to the n from here again. Lower limit doesn't contribute. And finally here, once again, so this integral is simply again a 1 over minus in. So this gives you minus 2 over n square product, and then the e to the minus in theta evaluate between these two, right? So that gives you minus 1 to the n minus 1. Okay, that's the answer. So there are lots of terms here. I mean, you can see there is a n square, n cube. I mean, there's a n here, n square here, n cube here. So lots of terms here. So that's for fn. And for f0, that's more straightforward. f0 is simply 1 over root 2 pi integral d theta theta square from 0 to pi. But this is simply theta cube over 3, right? So this gives you theta cube over 3 evaluated between pi and 0. So this gives you pi cube over 3 root 2 pi. It's a bit of a mess. So let's sum this up. So there is a 1 over root 2 pi times f0. So that means 1 over 2 pi times pi cube over 3. That's the first term, f0 term. I'm summing over now the series. I mean, I'm taking 1 over root 2 pi fn e to the in theta summed over n. So this is the f0 term from here. Then from the remaining parts for n not equal to 0, you get here 1 over root 2 pi, 1 over root 2 pi is again 1 over 2 pi. And now there are lots of terms. So pi square minus I n minus 1 to the n plus 2 pi over n square minus 1 to the n, and then minus plus 2 over I n cube minus 1 to the n minus 1. This whole thing multiplying e to the I n theta for n not equal to 0. That's the expression. Right? So, I mean, you can again check now what happens at theta equal to, for example, pi. Huh? Maybe we can, or theta equal to, so I don't know whether I can, let's see if I can get this. So theta equal to pi, so this is what you find, eh? This is the Fourier series you find. But now let's try to evaluate this for something. For example, at theta equal to 0, you just, this guy all becomes 1, so you have just said this sum, and that whole thing should be equal to 0 on the other side, right? So take theta equal to 0, f of theta is 0, because this here it's continuous, between 0 and is continuous. So you just get 0 here, so 0 should be equal to all that at theta equal to 0. Okay. This gives you one identity. Then if you look at theta equal to pi, you get theta equal to pi, there is an extra minus 1 to the n here from here. So you get, okay, so then you get another identity which is 1 over 2 pi, so pi square over 6 plus 1 over 2 pi times pi square over minus I n. But you see this guy is cancelled, right? This will cancel, the odd ends, because I have to here summation over both positive and negative n. Okay? For theta equal to 0 or pi, this will cancel, because theta equal to 0 or pi, e to the I n 0, e to the I n or e to the minus I n is the same answer. Okay? So when I sum it up, this will become, the odd powers of n will vanish. Is that correct? I mean I have to, this sum includes both positive n and negative n, right? So the sum of the two things, positive n and negative n, will vanish if it is odd function in n, right? Of course, in general, it is not an even or odd function because there is e to the I n theta, right? But theta equal to 0 and pi are special cases. For theta equal to 0 and pi, theta equal to 0 there is always 1, whether it's n is positive or negative is always 1, right? Whereas for theta equal to pi is always minus 1 to the n. It doesn't matter whether n is positive or negative. Okay? So this function becomes, I mean, this becomes even for theta equal to 0 and pi, even in n for theta equal to 0 and pi. So wherever you see odd ends in the remaining pieces, that should vanish. Okay? I mean, that cancels. So what is left over is only even piece. So you get, so where is it? Yeah, here. So I don't need to use this. So you get here 2 pi over n square, minus 1 to the n, minus 1 to the n has cancelled, and then and summing over the positive and negative, you get an extra factor of 2, right? And now I have a sum simply n positive, okay? Because the negative gives you the same as the positive numbers. So which is what? Which is equal to pi square by 6. Okay, 2 pi cancel, so this is simply plus 2 sum over 1 over n square. Okay. Now this is supposed to be equal to what? Pi square by 2, right? This is equal to pi square by 2. This is an identity. On the other hand, let's look at theta equal to 0 term. So there, this is 0 because here it is continuous, theta equal to 0, right? I mean, this also at theta equal to 0 is 0, here also it's 0, so it's continuous. So 0 is equal to pi square over 6, I mean the first term. Once again, it's odd guys cancel, only the evens survive. So this gives you again plus 2 pi cancels, 2 over n square summed, but this time I have a minus 1 to the n, right, because n is theta is 0, so this doesn't give you a minus 1 to the n. So there is a minus 1 to the n here. So you have two different identities now. Okay. I mean, so this gives you, if you take this pi square over 6 here, so 1/2 minus 1/6 is 1/3, right? And then divide by 2. So one identity is sum over 1 over n square is equal to pi square divided by 6. Huh? Because there's a 2, I have to divide by 2.
1 of minus 1/6 is 2/3.
1 of minus 1/6 is 1/3. I mean, it should be something less than half, right? Huh? Sorry? So, okay, there are lots of funny identities you can get. Yeah.
I want to know just on the continuity of function. When you write
F of theta, yeah.
pi square pi over no 6 over 2
Yeah.
equal this because the function
The result of the Fourier series, yeah.
is continuous. How you take because this function is even, no?
This is what?
This function between 0 p.
Yeah, so this function I'm defining like this. From it is 0 between minus pi and 0. Between 0 and, so it's here it is 0 from here to here, minus pi to 0. But here it's a theta square, so it goes like that. Huh? I mean, here it's pi square. So theta square, quadratic function.
When you consider pi square over 2,
Yes.
you take
F pi plus F minus pi, yeah, divided by 2.
The two function 0 between p and minus.
Yeah. This is the same as F of pi plus F of minus pi divided by 2. That is what the theorem says, right?
Because the function is
Yeah, exactly. Okay, so there are these various identities. I mean, okay, I mean, you could try to prove some of these things. You know, I mean, maybe I could just give you an indication of how you will try to prove this, and then you can try to, just for fun. I mean, also to use this contour integration to become more experts on contour integrations. So, I mean, suppose I want to compute something like 1 over n square. This is, of course, n greater than 0, right? N greater than 0, n equal to 1, 2, etc. Right? Suppose I want to compute something like this. I mean, how will I do this? I want to use also the contour integral methods, residue theorems, type of methods. Suppose I want to do that. So if you look at this thing, so here is my 0. But what I'm summing over is from 1, 2, 3, etc. Right? But this is, of course, even. So in fact, I could make it all integers, plus and minus integers, but except n not equal to 0. Okay? Divided by half. Correct? Because minus 1 is the same. If n is minus 1 is the same thing, I'm just counting twice. So I will just sum over all integers except 0, because 0 blows up. No? Okay? But this I could think of, I mean, suppose I could write down some function which has, poles exactly at all the integers, and it has a residue which is, say, at a given integer n, it has a residue 1 over n square, right? Then I can, evaluate this thing, right, as a contour integral. So I need a function which has poles at all the integers, and the residues being 1 over n square. Okay. So let's see how. So one function you can construct is so consider this thing, cosine pi z divided by sine pi z. Okay. So this has you see, for every integer z, this goes to 0. Sine pi times any integer is 0, right? And when you look at the residue, I mean. so if you make an I mean, so let's look at near z equal to 0. I want to look at how I mean, in other words, see if you look at sine pi z, how does it go? So let's say z is the real line. So sine function is like this, right? It keeps going like that. So at z equal to 0 sine pi z, near z equal to 0 sine pi z is simply approximately equal to pi z, right? I mean, there are series, but the leading term is that. But if you look at, this is near z equal to 0, near z equal to 0. But if I look at near z equal to 1, so we are looking at sine of pi, say 1 plus z now. Okay? So near z equal to 1, so write z as 1 plus z. So then sine of pi plus pi z, but sine of pi plus anything is minus sine z, right? So you'll get a minus sign here, an extra minus sign here. Here you'll again get a plus sign. So this will give you a minus 1 to the n. So this behaves near z equal to n. This behaves like pi z times minus 1 to the n. Right? That's the leading term. Okay? I mean, what I'm saying is, so you want to expand this at say one of the integers. Okay? So you want to write this as z equal to n plus z minus n. If I'm looking at the position, the pole at z equal to n, you want to make an expansion, Laurent expansion, right? That's what you want to do. So let's see. Maybe I erase this here. So I want to study what happens near z equal to n. So I'm going to make a Taylor expansion here like that. So I can write this. So sine pi z is the same as sine pi n plus pi z minus n. Correct. I just added and subtracted n. I didn't do anything. Okay. But this is what is small, because I'm making expansion in this. Z minus n is small, right? So on the other hand, you know that sine of pi n plus any angle, anything, any quantity, is the same as minus 1 to the n times sine of pi z minus n, right? No. There's I mean, sine of pi plus theta is minus sine theta, but sine of 2 pi plus theta is the same as sine of theta, right? So whether it depends on whether n is this n is even or odd, you pick up a sign. So there's a minus 1 to the n times sine pi z minus n. Now when z minus n is small, we can make a expansion of this quantity. So this guy goes like pi z minus n minus pi z minus n cube over 6 factorial cube over 6 and so on, right? The expansion, the Taylor expansion for the sign. Okay, so that's, but the leading term is of course this. Okay, so this goes like pi, so this guy behaves like minus 1 to the n times pi z minus n, because near z, when z minus n is small, these things are very small compared to that. So, whereas cosine pi, if you do the same thing, cosine pi, so again write z as n plus pi z minus n. Cosine of pi plus n, cosine of pi, so this guy have a Taylor expansion. Okay, I can just write it as cosine, what shall I write? I mean, cosine of pi n is plus or minus 1. I mean, suppose z was exactly equal to n, okay? Then you just get cosine of pi n. So when you make a Taylor expansion of this object, it will start with the first term will be simply cosine of pi n, which is minus 1 to the n, right? So this gives you minus 1 to the n plus order z minus n, right? The leading term is minus 1 to the n. So that minus 1 to the n cancels with this minus 1 to the n, and you just get pi times pi over z minus n, right? So this function, so cosine pi z over sine pi z, has the property that it has a pole at every integer, right? with the, okay, if you want to get rid of this pi, okay, we can multiply by this pi. Huh? Okay, so this function has a property that it has a pole at every integer, right, and with the residue 1. Okay. So if I want to, if I can get this residue by just considering a function 1 over z square times pi cosine pi z divided by sine pi z. Consider this function. This will have, okay, if you include also the half, this is that. Yeah. This will exactly give you the residue if you consider the what is the d minus 1 coefficient in the Laurent expansion of this term. That's exactly this quantity, 1 over n square. Okay. So if I take this function, let's call this function something, I don't know, h of z equal to that, and integrate it over this kind of a contour. So let's see. So here I have the thing here. This is 0, 1, 2, etc. Okay, and here it's -1, -2, -3, etc. So you remember in this sum n is not equal to 0, so I should exclude n equal to 0, right? So I can consider a contour like this. Okay. This contour, this will give you, and then you can, okay, so suppose I first sum up to capital N, sum capital N, and then I will take the limit capital N to infinity. So then I have to take a contour which encircles up the first n points, no? And then here the n plus 1 is outside. Similarly here up to minus, so minus n to capital. So this is, let's take minus n to plus n with the n not equal to 0, right? That I have to exclude. Okay, so here it's up to minus n. So I close the contour here. Okay. But then I can rewrite this contour. I can, so here is my contour integral. This is a counterclockwise, right? And that the result of this integral will be simply that sum. So I'm integrating h of z dz over this contour plus that contour. That will give me this sum. Okay. But now I can deform the contour and consider from here. I take this upper thing here, and also here down. Okay. So the contour will be. So I mean, yeah. So consider this whole thing like that. So it comes like this, comes like that, then comes like this, comes like that, like this. Huh? Provided you can be sure that this part of the integrals do not contribute, right? That is, this is not exactly Jordan thing, but it's very similar. You can show, because you see this guy is always, no matter, I mean, you remember why the Jordan lemma worked. The main reason for Jordan lemma to work was if you had, remember, there the function was e to the I z, e to the I alpha z, where alpha is positive. And then times any function, f of z, which had the property that it was vanishing uniformly at infinity and so on, right? Now, this integral from in the upper half was vanishing. Upper half circle was vanishing. Why? Because in the upper half circle, so in the upper half circle, sorry, the z has a real part x plus iy, where y is positive. That's the point. In the upper half, y is positive. So when you plug that in here, you get. You see, this just gives you a face, so that's not important. But this guy, because it gives you I square, it gives you minus alpha y. So if alpha is positive, you should choose positive y to get exponential suppression, right? Whereas if alpha is negative, you should choose negative y, so lower half plane, right, to get exponential suppression. Okay. Now here again, the same thing happens. I mean, here you see. The suppression is already because of z square. The z square is already sufficiently strong, fast to. This is not an exponential suppression, but this is just a power law suppression. But that's again is enough to show that there's no contribution here for the large radius, right? And this one goes to essentially 1 because whether it's the upper half circle or lower half circle, it doesn't matter. Why? Because this is e to the I pi z plus e to the minus I pi z divided by e to the I pi z minus e to the minus I pi z up to a factor of I. This thing is that. Now suppose I'm looking at z in the upper half. Okay, then this is exponentially suppressed, this is exponentially suppressed. Those are exponentially blowing up, but they are blowing in the same way. So you see, this guy is much larger compared to that, right? In the upper half part. So in the upper half part, you can ignore these terms because those are exponentially increasing, right? But then it's the same, up and down is the same, so they cancel, right? And similarly, if you go to the lower half plane, this guy is exponentially suppressed and that guy is exponentially blowing up, right? But again, they are equal up and down, denominator and numerator are the same, right? So they will become one. So in both the upper half plane and lower half plane is going to be some constants. It will not blow up, either side. But there is suppression because of z square, 1 over z square. So this object will not contribute on this upper half circle and lower half circle equally. Okay, so you can just add this part of the contour. It doesn't change anything because that's 0 anyway. But now you see I can deform the contour, open up, and then the only pole here that h has is at z equal to 0, right? So therefore, this contour integral by contour deformation is the same as now maybe I'm not sure if I'm doing the signs correctly. Yeah, I mean this looks to me it's a clockwise, right? Because from when you deform this contour, it will just become like that, right? So it will be like clockwise, I think. So it's a clockwise contour. Let's say this call it C tilde contour of the same function h of z dz. Okay. So we just have to evaluate at z equal to 0 pole. But z equal to 0 pole is a little bit more tricky because there is a pole coming from sine pi z, but there is also z square. So it's a third order pole. So you have to expand. You do it to compute the. You have to compute the residue of that. Okay. Actually, what is the? We can try. We can try that. Let's see. So I'll need to go beyond this, right? So at z equal to 0, cosine pi z is pi z 1 minus pi square z square over 2. Okay, that's enough. I don't need to go beyond that. And sine pi z is pi z minus pi z cube over 6, right? Expanding near pi. I need to only go, because of z square, I just need to go up to z square order in the expansion. That's enough to get. And now I can just, so let's take out, and then there is here pi over z square by 2, pi over 2z square. Okay. Here I can take out pi z as a common factor. So this becomes 1 and that becomes 2. Okay. So I can now expand it. So this gives you, pi cancels, so 1 over 2z cube. And here you get, this is a product of two things, 1 minus pi z square over 2 from there. And this you do a expansion, the geometric series expansion. So this gives you 1 plus pi z square over 6. And it's enough to keep up to that point, because this is z cube, you see. If you go to the z to the 4, that's not going to give you a pole, right? A singularity. So it's enough to do that. So you get here 1 over 2z cube, as that's a leading singularity. And then at the 1 over z order, what you have? There's a 1 over 2z. And then here, there is this term pi z, this times that plus that times that, right? So here you get a minus half plus 1/6, which is minus 1/3, right? So you get here minus pi square over 3. Okay, that's the thing. So sorry, this is the original sum was 1 over 2 pi I times this. So this is 1 over 2 pi I, because I want to take the residue. Residue is there. So this just computes the residue, which is actually pi square over 6, right? And the minus sign, because this is clockwise. So this really gives you pi square over 6, which is what we had, I think, if I remember correctly, right? It was there, yeah, correct. I mean, although we have taken the sum up to n, I mean, you really have to take the n goes to infinity limit, because we said this integral I can ignore, but only if the radius is infinity, right? For a finite n, it's not 0, the integral, right? So it's only in the n goes infinity limit that you will get that. Otherwise, there will be extra contribution from here, right? I mean, the full answer will be this plus the suitable, the circle contributions, the circle contribution, right? But this circle contribution will vanish in the large n limit. So that's it. So this is a very, I mean, many of these sums involving integers, the trick is to write some function which gives you the residues, which gives you poles at all the integers, no? And then you cook up the precise function to produce the correct residues, no? And you can try to do this integral.
Can we use gamma functions because they have poles out?
Sure, you can also do that. But gamma function, okay, there will be only negative integers, which is fine. So you can write it as gamma of minus z. But gamma of minus, they have but the residues comes with the factorial ends and so on, no? So may not be very useful. I mean, unless in your problem there are factorial ends, you know, then okay, then gamma function is a natural thing, right? You could try using similar trick for the previous example. In the previous example, and I mean, and not just for theta equal to 0 or pi. I mean, you can try to do it for arbitrary theta. I mean, this should be for theta equal to pi. This function was discontinuous, so we got, that's why we had an average. We took the average, f of pi plus f minus pi divided by 2. Theta equal to 0, this was continuous, so we just took this value 0. But in between, so for positive theta between, I mean, strictly between 0 and pi, this should just give you theta square. Can you reproduce that? Huh? That would be a good thing to try. Huh? I mean, now I have erased what was the original function. But okay, I mean, you have to go back there. But I mean, in principle, you should be able to do it. Huh? If you cleverly find the function whose residues are the right ones. Okay, I think I'll stop now. I wanted to do Fourier transforms also, but I think I'll do that next time.